This is section 7.3, and we are going to find volumes of solids using what's called cylindrical shells, or what's called the shell method. The first sentence here says, as with anything, we run into a problem when volumes with volumes of certain functions. For example, find the volume of the region in the first quadrant bound by y equals negative x squared plus 4x when it is revolved about the y-axis. And this demonstration hopefully demonstrates the shape that's going on, and here we have the exact same equation, and we are really looking just in the first quadrant, and we're looking from 0 to 4. So let's revolve it around the y-axis. And there it is. There's the shape that's formed. The problem is if we use the methods that we've used so far, it's going to be pretty difficult to find an answer for this, especially integrating along the y-axis. If we stop this, look at the function, if we're going to use just revolving it, and let's say we're using the washer method, the right function would be negative x squared plus 4x. The left function would be the exact same thing, and when we subtract the two, you're going to get a radius of 0 the entire time. So we're going to have to come up with some other method to figure this one out. So let me revolve this again. There's the shape that's formed. Stop this. What we're going to do is called sweep the shell. There's a cylinder right here, and it starts with the curve, and we go around the y-axis, and it's a certain x value. Well, if we take the area of this cylinder, then the area of that cylinder, and the area of that cylinder, and the area of that one, and we add up all the areas of all the cylinders you could possibly have going along this curve, then we're going to come up with the volume of the solid. So that's what we're going to try to accomplish. Let's go back to the notebook. Here's the problem again. It's the exact same problem. And what we find out is, well, I graphed it a little bit, and really what we're doing is we're picking an arbitrary x. Here's one of the curves, and I've rotated 180 degrees. So let's say we pick some arbitrary x, maybe right there. And I'll go to the same place on the other side, roughly. And we're going to create a cylinder. And it represents rotating this graph around the y-axis. And there it is. Now we're going to find the area of this rectangle. The area of this cylinder. The area of the cylinder is 2 pi RH. Now, we're going to integrate from 0 to 4, because that's the zeros in the first quadrant, and 2 pi RH. Well, we want it in x. We want the equation in x here. Now, the arbitrary x that we picked, it's the radius of the cylinder right here. So any x value is going to be the radius of the cylinder. The height of the cylinder is going to be represented by the function value, or in this case, negative x squared plus 4x, and then the dx. Here's the setup. And from this point on, I'm sure we can do the integral. I pulled the 2 pi out, distributed the x through. You get negative x to the third plus 4x squared. Here's the antiderivative. And we plug in the 4. And there's no need to plug in the 0 really, because both of these would be 0. And after a little bit of simplifying, a little bit of common denominator, we get 128 over 3 pi. And that's the volume of the solid. Okay, let's see the next example here. Find the volume of the solid defined by y equals sine of x from 0 to pi, rotated around the line x equals negative 2. Well, let's graph this. And you can ignore the integral for right now. The graph of y equals sine of x is sitting right there from 0 to pi. And there's the line that we want to rotate this around. Well, we would make a cylinder by rotating it, I don't know, about that far. This is an arbitrary x, and the cylinder would be formed by rotating it all the way around this line. So there it is, and we'd rotate the bottom piece all the way around. and there would be roughly your cylinder, very roughly as a matter of fact. So we're integrating from 0 to pi. That's the two zeros in the first quadrant. And once again, the area of the cylinder is 2 pi RH. R is, in this case, not just the arbitrary x value that we have, because that would just be from 0 to x. We have an additional 2 off to the left. So the radius of this cylinder is 2 plus whatever the x value is that we happen to be on at the time that we're finding the area of the cylinder. So we have x plus 2 as the radius, and the height of the cylinder is the function value. Once again, in this case, it's sine x. So now we integrate. I've pulled the 2 pi out. We're integrating from 0 to pi. I used tabular method because the x plus 2 would eventually go to 0. Remember, we take the derivative of this function, we take the antiderivative of the other function, and then we do the diagonals. So it ends up being 2 pi times negative x plus 2, the negative because the antiderivative is negative cosine x, and plus sine x, because you have negative negative, that would be plus 1 times sine x. And we're evaluating that from 0 to pi. After plugging in some values, simplifying, I end up with 2 pi squared plus 8 pi.